minute recap on what we've done up to now. We started off, we introduced the concept of the partial derivative of a function of two variables there, but okay, need to keep the chat down. Thank you. A function of two variables there, but the principle generalizes to functions of any number of variables. It has a definition in terms of limits which is very similar to the definition for the derivative of a function of a single variable that we met last year. So it's the limit of the relative change in value of the function between 2 points as one of the points gets closer and closer to, say, the fixed base point. What you're seeing here is a function of two variables, and it's the y variable, the second variable, that's changing. So on the top of the fraction, we have the difference in value between the function at the base point, xy, and the nearby point, same x-coordinate, y plus delta y. But it's relative to the change in value, delta y. And you're taking the limit of that quantity as delta y converges to 0. And that gives you what we interpreted as the rate of change of the function at the base point xy in the direction of the y-axis, or in the direction parallel to the y-axis. There's a similar one for the x-coordinate as well. In practice, we obtain partial derivatives of functions of various kinds by employing this principle here. The basic idea is, well, when we're looking for a partial derivative with respect to one variable, let's just for the moment say that's x, then any other of the variables we treat for this purposes as if they were constants. And then the function we're looking at really becomes a function of a single variable x, if we are temporarily regarding the other variables in the definition as constants. So we got a function of a single variable x again, and then we just differentiate that as normal, using the normal rules, product rule, chain rule, quotient rule, etc. Normal principles of differentiation, all the while treating the other variables as if they were constants, and carrying them through as constants through to the resulting function. Okay, we looked at several examples of that, and there are exercises here. There's a bit more terminology attached to higher order partial derivatives, etc. We did various examples, and there was an extra problem handout which contained lots of the questions we're looking at, significant differential equations or partial differential equations, and verifying that the given function was indeed a solution to them. So finding the partial derivatives of the functions and putting them back into the equation. So we're going to continue in these lectures to develop the theory of differentiation of functions of more than one variable, and also their integration. And so the next thing to do is to look at another aspect of the graphical interpretation of these quantities, and talk about the tangent plane to a surface. So first of all, I'll just remind you about the one variable case. So in the one variable case, we have a variable x, we have a function f of x, and at various points there, we can talk about the tangent line to the graph of the function at the point A. Okay? So this is the tangent line to A, and the tangent line at A has slope that's given by the derivative of the function evaluated at x equals A. Okay? And these tangent lines exist at all these points where the function is differentiable. And these lines give you the best linear approximation to the behavior of the function at that point. If we had to substitute, rather than the original function f, if we had to replace the function f by some straight line at this point here, which straight line would you choose? Which straight line best reflects the behavior of the function at this point, at values close to this point? Well, it is the tangent line, the function that has the same rate of change as the original function at that point. But this is all for functions of a single variable. What we'd like to be able to talk about is a similar concept, but for functions of two variables. So for functions of two variables, the domain is a copy of R2, here denoted as x and y. So you think of this as the ground floor plane. And then we have a third axis, which we might refer to as the z-axis. So we've got the floor, which is the xy plane, got the z-axis going up the corner of the wall, so to speak. And if we've got a function of two variables, and we assign the value of the function evaluated at x and y to the third variable z, then what we're looking at is this. It's a nice, continuously changing function. Then we've got some kind of surface defined by the function. And there might be some, would be xp, yp. And this would be underneath some point, let's just call the point in general P, and this point would have z-coordinate zp. We're trying to build up the analogous picture to the one variable case. And what we'd like to be able to do is to replace or think about, rather than the original function, the original continuously changing surface, think about what kind of linear surface would best approximate the function at that point. So the generalization of a line in two dimensions, if you're talking about a three-dimensional total environment here, the thing to think about is a plane, a flat plane. And we want a flat plane which goes through the point P and which best approximates the behavior of the function at that point. And what we mean by that is that if you go along the x direction along the plane, go along the y direction along the plane, so those are kind of like two linear directions across the plane, that the gradient or the slope of the plane in those directions is the same as the rate of change of the function, the original function f, in those directions at that point P. Okay? So where a line, you can have a tangent line to the graph of a one variable function. The graph of a two variable function is a surface, and the corresponding thing to the line is to talk about a plane. Okay, so a tangent plane. So this is what we're talking about. The tangent plane to the surface. So what we'd like to describe is how we can obtain the tangent plane, meaning how we can describe it through an equation for the plane. Because remember, planes in general, planes in R3 in general consist of the set of points x, y, and z, and they've got some defining equation. So there'll be a ux plus v y plus wz plus uvw rs plus a constant s equal to 0. Any plane in R3 can be described by some kind of equation like this. A linear equation in the three variables x, y, and z, fixed real coefficients, some kind of constant term, and this equation equal to 0. Okay, so this is what's sometimes called the Cartesian equation for a plane in R3. So the question that we'd like to answer and to describe is how you go from the formula of f to the equation to define the tangent plane. How can we give the description of the tangent plane and show how all the various parameters, and there's 4 of them to find here, I think. Yeah, 4 of them defined there. How they all relate to the function f. Okay. The tangent plane is attached to the behavior of f, so the description of the tangent plane should come from the description of f. Okay, and it's described how it's done here. So I think I've built up this diagram more or less to fit what's going on here. So we've got a point P, which is on the surface. So S is the surface described by the function z equals f of x and y. P is this particular point on the surface with coordinates xp, yp, zp, as shown in the diagram. And the tangent plane is going to have this kind of equation. So that equation in 1.26 is just an equivalent version of this, where we've left just where you make z the subject of this equation. So you leave z on the left-hand side, put everything else over the other side, and rescale by 1 over w. So you get an equation of some type, which is z equals some linear combination of x and y and a constant. Okay, we would hope to be able to find this equation, and by find this equation we mean find the alpha, find the beta, and find the gamma, all in terms of information coming from the function f. Okay, so that's the task. Everybody see the diagram? Okay, it's a bit small, I know. So got the xy plane at the bottom, the surface S, tangent plane T, the point P which lies on the surface and the plane, and P is coordinates xp, yp, and zp. Okay. Well, we approach this, we can talk about the alpha and the beta first. You see, by definition, the tangent plane is giving you the instantaneous behavior of the function at that point P. The tangent plane is the same orientation in R3. And remember, you've got a plane going through. You've got a plane going through a particular point. Imagine the point P being right on the end of the pen there. If you've got the point P on a plane, well, the plane can be oriented in any number of ways and still go through the point P. So the question is, what kind of orientation does the plane have? Well, if it's the tangent plane to the surface, the orientation of the plane should be in such a way so that the gradient of the plane in the x direction, or the gradient of the plane in the y direction, matches that of the surface of the function. Now, the gradient of the plane in the x and y direction, in terms of this equation for the plane T, those are the quantities alpha and beta respectively. Okay? Alpha is the gradient of this plane in the x direction, beta is the gradient of it in the y direction. If that's going to match the surface, then we should have that alpha is dz dx and beta is dz dy. Or because f is equal to z is equal to f of xy, this should be the x derivative of f evaluated at this base point xp yp here. That should give us alpha. And when we take the y derivative of f and evaluate it at the base point xp yp, that should give us the beta. Okay. So that's where the alpha and beta are coming from in terms of f and in terms of the base point. Then we just have to settle for gamma. Well, gamma fits into an equation like this because the point P is lying on the plane. So when you put the coordinates xp and yp into the equation of the plane, we should get out zp, the height of the point P. Okay, we feed in xp, yp, multiply xp by alpha, yp by beta, add on gamma, which we don't know yet, we're trying to find gamma. Add on gamma, whatever it is, this should give you this point up here, zp. But the point is also on the surface. So that value zp is exactly f of xp, yp as well. Okay? Because this point P is on the tangent plane, but it's also on the surface as well. Okay? So at the same time, this quantity zp is equal to all this in alpha, beta, and gamma is equal to f of xp, yp. So by turning that equation around then, just making gamma the subject of this equation, putting everything on the other side, we get the gamma is f of xp yp minus these two quantities, minus alpha xp minus beta y. So again, that's the solution to the problem at hand. The problem we started out with is how to determine the equation of the plane in terms of information coming from the function f. Alpha and beta were the gradients of f in the x direction and f in the y direction, and gamma comes as this combination here. So it's all coming in terms of information about f and evaluated at the base point xpy. Okay? Part of the inputs into talking about this tangent plane t as well. So that shows you how everything about the tangent plane, the alpha, beta, and the gamma, they all come from f and the base point coordinates xp and yp. Okay, so we could go through an example of this. I think unfortunately there's a misprint in the notes here in the solution of this example. So we'll just go through it and we'll correct it as we go. Let me just record this. Okay, so we're looking at example 1.5. So we got our function f of xy. This is x squared y plus 2y squared plus x plus 1. And we're seeking we want the equation of the tangent plane to the surface of f, the surface defined by f, at the base point 2, 3, I think it is. Okay, so I think there's a misprint along the way, so we'll correct that as we go. So we're looking for the equation alpha x plus beta y plus gamma, looking for the equation of this type. Finding it means finding the coefficients alpha, beta, and gamma. Okay. Well, from what we've looked at, the alpha is going to come from the partial derivative of f with respect to x. Looking at the equation defining f, this becomes 2xy plus 1. And we also need the partial derivative of f with respect to y, which will be x squared plus 4y. Each time, so for x, you're treating the y variable as if it were a constant. You get 2xy plus 1, the 1 coming from the x. And then for the dy, you're treating x as if it were a constant. When you evaluate this at the point 2, 3, we get, well, 2 by 3 is 6, so it's 12, so it's 13. So we get 13, and that's equal to alpha. And here it's 4 plus 12, so here it seems to be 60. And that's the quantity beta. Okay, so it's a slight misprint. In the notes it has 12 for alpha. That's incorrect, it should be 13. Yeah, it's in the partial derivative. So you need to correct this partial derivative in the notes as well. And then the constant coefficient gamma This comes from this equation here. We basically flip this equation around. So gamma will be z minus alpha x, beta y, at every point in the plane, and we just focus on this particular base point. Okay? So we evaluate this equation at the base point 2, 3, so that gives us values for x and y. And what do we know from z? Well, z comes from the value of the function at that base point. So this is going to be f of 2, 3 minus alpha, which is 13 times 2, minus beta, which is 16 times 3. Just whatever it is, so it's 4 by 3, 12, plus 18, 13, 22, so it's 33, I think. Correct me if I'm wrong, minus 26, and minus 48. 33 minus 26 minus 48. 7. Is that correct? Minus 26 is 7. 7 minus 48 is minus 41. My arithmetic correct there, I think? Okay, so that would mean, so the tangent plane would have equation z equals 13x, 16y, sorry, minus 41, minus 41. That's different from the minus 37 in the notes as well. So you need to correct that too. Okay, so is there any questions about? Okay, so it's kind of more interpretation of the meaning of the partial derivatives, if you like. Talking about the geometry of the situation, the graph, the surface defined by the function, and this function having a linear approximation in a way, which is the plane going through a particular point which best approximates the behavior of the function at that point. And this is going to be what we call the tangent. Okay, so you'll see on the following page then we've got a set of exercises which we were working on in the tutorial last week. So if there's any of those that you haven't been able to complete yet, do keep working on those and do seek to get some help with those from your tutor in the tutorials this week if you haven't completed them all. So any questions about any of the exercises there? Yeah. Okay. So next in the notes we have this section on what's called total differentials in the small increments formula. Okay. Yeah. Little triangle is the Greek letter delta. Capital Greek letter delta. It's normally used for a change in value. Okay, so we're talking here about total differentials in the small increments formula. Really what we're interested in is the small increments formula, which we'll get to in a moment. And up to now, when we've been talking about partial derivatives, we've talked about it, especially for a function of two variables, we've talked about it as a process where you're looking at the rate of change of the function when one of the variables is changing. One or other of the variables is changing. But now we want to think about capturing what's going on when both of the variables might be changing. Okay, and this leads us into this section on total differentials. So what is a total differential now? There's a bit of theory here at the start. A total differential is an expression like this. Delta F, so this is the Greek letter delta. You might triangle, that's the capital delta. So delta F, delta is normally used to denote a change in something, the change in value of some quantity. So delta F is a single quantity representing the change in value of the function f. Delta x and delta y are the changes in the variables x and y, respectively. So delta f is formulated like this. It's the difference in value between evaluating f at some point which is nearby to this base point xy. The x variable is varied by a small amount, delta x, and the y variable is varied by a small amount, delta y. Now, a total differential, it's a kind of it's a thing which is attached to nicely behaved functions. Okay? So as long as our function is nicely behaved, it'll be true that this change in value of the function f can always be reformulated in this kind of way. So what we're seeing here in this equation, in equation 1.39, is delta f, the change in value of f, being expressed as some function times delta x plus another function times delta y. And these two functions, a and b, are both functions of the two variables x and y, perhaps. These are the main parts of this expression. These other two parts, this lambda delta x and mu delta y, those are these kind of small correction terms or small error terms. And the property that these coefficients lambda and mu have is that they both converge to 0 as the changes delta x and delta y converge to 0. So that in the limit, as you look at points which are ever closer and closer to the base point xy, so as you let these changes delta x and delta y converge to 0, the limiting behavior of this change quantity is really this function a, whatever it is, times delta x, and this function b, whatever it is, times delta y. But those two functions are evaluated just using information from the base point. They're just evaluated at the base point xy, for this one, and similarly for b. Now these functions, capital A and capital B, are not some strange kind of new function that we haven't talked about. They are exactly the partial derivatives. So just skipping forward slightly to this theorem down here. This theorem says, well, if the function is nicely behaved, now nicely behaved means that the partial derivatives exist and that they're continuous functions. So there's no sharp edges to the surface defined by the function. There's no instantaneous changes in the rate of change of the function. The partial derivatives are continuous. In that case, the function does have a total differential. You can express the change in f as a function times delta x plus a function times delta y plus this kind of error term here. which is a product of this quantity lambda multiplied by delta x and delta y, and the lambda is the property that it converges to 0 as delta x and delta y go to 0. But these two functions, the functions multiplying delta x and delta y, are these familiar functions which are the partial derivatives of x and y respectively. So that's going to be the case for all the functions that we're going to be encountering in this. Okay, we're going to be encountering these nice functions which have these partial derivatives. Partial derivatives are going to be continuous for them. So we'll know that this expression with the total differential exists. Now, the use we'll make of it, but we'll make a few different uses of it. But the thing we're going to focus on now is what we can do with this equation when we consider the delta x and delta y to be very small. So if you're talking about a nearby point to the base point x1. Because the lambda is converging to 0, if we're sufficiently close to the base point, this error term here is going to be very small. And will be, it'll be a legitimate step to say that the change in value of the function is approximately equal to the sum of these first two terms. Partial derivative of the functions of the function evaluated at x and y, these two coefficients just multiplying the change delta x and delta y respectively. And that's what's known as the small increments formula. So it appears here at the end of the proof of that theorem. I think next time we might look at the proof of that theorem. But this equation here, 1.56, is the one I want to highlight to you. And hold that up as the important kind of thing to focus on. So this says, at a nearby point to the base point xy, so delta x and delta y are the differences, the kind of offsets from the base point xy. The change in value that the function undergoes between the base point xy and the nearby point, x plus delta x, y plus delta y, the change in value that the function undergoes there can be approximated by this linear expression in the changes delta x and delta y. The coefficients of that linear expression are the two partial derivatives evaluated at the base point xy. That's what's known as the small increments formula. It has a generalization, the obvious generalization to situations where there's more than two variables. Okay, if there's an xy, if there's a z as the variable as well, you can just imagine adding on a term here, delta z times the partial derivative of f respectively. Okay, and adding on one of those terms for whatever number of variables the function has. So that's this thing indicated here. So if your function is a function of n variables, x1 through xn, this is the small increments formula for that function. At a point close to some base point, x1 through to xn, we can approximate the change in value of the function as the sum of all these linear terms, where the change in the ith variable is multiplied by the derivative of f with respect to the ith variable evaluated at the base point. So to give an example of one way to use this, or one way to make use of this concept, is in a little experiment here. So you're familiar with the idea that the way gravity works close to the Earth's surface is that it accelerates objects towards the center of the Earth at a certain rate. And by carrying out experiments, you can realize that the rate of acceleration is the same for all objects. It's independent of the mass of the objects. And you can really observe that when you look at it in a vacuum. If you disregard the effects of air resistance, this is what, when they went to the moon, they did this classic demonstration where they dropped a hammer and a feather on the surface of the moon, and they both fell to the ground on the moon at exactly the same speed. They won't inert due to air resistance, but if you could do that in a vacuum, the hammer and the feather fall at the same speed. So you can describe the action of gravity if you know this acceleration due to gravity. Now, by observation, you can get a very rough approximation for the acceleration due to gravity here on the surface of the Earth, and everybody probably knows the approximation 9.8 meters per second. But just by simple observations, you might estimate that as something close to 10 or something, right? But if you want to get a very accurate estimate of it, you want to measure very carefully and have some kind of rigorous experiment. So one of the early experiments that they did for working out this acceleration due to gravity was to look at the motion of a simple pendulum. So a simple pendulum is this kind of setup where you've got some mass on the end of a string or the end of a light solid rod, and it's supported at a point here, and it can freely swing back and forth, just like the pendulum on a big old-fashioned grandfather clock or whatever. Okay, so you just pull it aside, and it swings back and forth. Of course, the thing that's keeping it swinging back and forth is the action of gravity. As the mass gets up high, it gets dragged back down again, then it builds up momentum, and it keeps going past the low point, and swings up again, and it does that. Okay? And if there's not a lot of friction in the thing, and it's a long pendulum, and there's a heavy weight there, it can keep going for quite a while. And in principle, if you could eliminate all friction and all air resistance, have it in a vacuum, and have zero friction, in principle, it would keep going forever. Now, the reason that this can be used as an experiment to measure the acceleration due to gravity is because of this relationship here. That the acceleration due to gravity turns out to be, when you analyze the physics, so when you analyze the physical laws of motion of that pendulum, turns out to be equal to this quantity. There's a constant here, 4 times the square of pi, times L over t squared. L is just the measure of the length of the pendulum, and t is the measure of the period of the pendulum. So the time it takes to make one complete swing. So one complete swing is, say, going from the high point on the left, starting there, all the way over to the right, and then returning again back to the start. So that's one period of the swing. From the start point, over to the other side, and back to the start point again. I think I've got, in a footnote there, I've got the derivation of that law from the equations of motion, but that's not our primary interest at the moment. The primary interest is just the existence of this expression. This shows you, if we take this as an equation here, this shows us that G is a function of L and T. So we can set up a pendulum, we can measure it very accurately, measure the length very accurately, set it swinging, and then make some accurate measurement of the time period t, time it takes to make one complete swing. And those can be fed into that formula to give you an estimate of the value of G. But of course, where the small increments formula comes in is that our measurements, if we're doing this very rigorously and scientifically, our measurements of L and T are themselves subject to uncertainty. Measurement error, or just some uncertainty in the calibration of the tools we're using to measure the length, and the stopwatch or whatever we're using to measure the time. Okay? There's always, these things are never 100% accurate, 100% precise. There's always error associated. Suppose we can quantify the error. So suppose we say, well, we've measured the length of the pendulum. It's a 2-meter length pendulum, but I've only got a certain amount of confidence in my ruler. It's going to be 2 meters plus or minus, what's that, 2 millimeters. 2/1000ths of a meter, okay? So I know that my pendulum is length 2 meters plus or minus, so some error within the range, plus or minus 2 millimeters. Similarly, when I time the time period, suppose I declare it to be 2.84 seconds, plus or minus 100th of a second. Okay. So some inevitable inaccuracy in declaring when it's done one full period, stopping the watch, and then some inaccuracy in the watch itself. What the small increments formula allows you to do is to quantify the combined effect of these measurement errors into what's the associated error range for our prediction of little g, for our prediction of the acceleration due to gravity. So we can work it out here. When we feed the figures 2 and 2.84 into the formula, we get this estimate for the acceleration due to gravity, which looks good, 9.79 meters per second. But the question is, what's the combined effect of these two errors? Now, you can probably work it out using just direct, naive means. But one good way to think about it is through the small increments formula. Because we can interpret those plus and minus amounts as being bounds on delta L and delta T. So delta L and delta T now become the errors in the measurement of L and T. So the error in L is somewhere between plus or minus 2 millimeters. So the absolute value of delta L is less than or equal to 2 thousandths. And the absolute value of delta T, the error in the time measurement, is no greater than 1/100th of a second either way. So this is what the small increments formula looks like for delta G. Delta G is the error in our estimate of acceleration due to gravity. And it's dg dl times delta L plus dg dt times delta T. And we're working here, we're assuming this formulaic relationship between the gravity and the length and T, the one we had at the bottom of the previous page. So we can obtain these two partial derivatives. 4 pi over t squared is dg dl, dg dt is minus 8 pi squared L over t cubed. So these get multiplied by the associated errors in L and T. And then here we're using the triangle inequality. Remember the triangle inequality from last year? Applied to real numbers, it says that whenever you add two real numbers x and y, see they could be negative, it's always less than or equal to the absolute value of x plus the absolute value of y. Okay, so this is the triangle inequality for real numbers. It's much more general, applies to vector space, certain kinds of vector spaces and so on. So we apply it here, and we're saying that the error in G has absolute value no greater than this quantity over here. So the partial derivative of G with respect to L, partial derivative of G with respect to T, multiplied by the associated bounds on the errors of delta T. We don't know exactly what the error in L is, the error in T is, but we're confident in the specifications of our equipment that they're no greater than those bounds. So then you can evaluate everything. The partial derivatives, they depend on L and T, and they get evaluated at the base point, 2 and 2.84. Those are our declared values for the measurement. So that's the base point. Then these quantities, delta L and delta T, well, we know they're no bigger than these quantities, 2 thousandths and 100. You feed it all in there, and it gives us this upper bound for the error in our estimate of G. So this estimate of G at 9.79 meters per second, the error bands from our measuring ruler and stopwatch or whatever, their combined effect produces a possible error amount in the absolute value of delta G. So we're going to say G is 9.79 meters per second plus or minus 0.079 meters per second. So that's good. It gives us a nice way of analyzing the combined effects of these errors, how they feed through and produce an associated error for the overall function. It also allows you to see which error might be having the greater effect. Because if you look at equation 1.65, you see here, you can look at these two terms, especially when you evaluate them at the base point. You can see which one is the greater. So if we did look at the numbers, what's the say, the time period. So it seems to be this one over here, which is having the greater effect. So if we had limited resources, if we did want to optimize our experiment and make the error in it less, this analysis would suggest that we'd be better off trying to improve our accuracy at the time measurement. That seems to be making a bigger contribution to the overall error for G. So that comes out of the analysis as well. So you can't see it there in the page, but when you put in the evaluations of these quantities at the base point 2 and 2.84, you can see that as well. Okay, that's good. That opens up the next set of exercises for us. There's a further example there, example 1.8, which you should read through and understand. And then there's a set of exercises there, exercises 1.2, which is all about using the small increments formula. Okay. So we could make the start on those at this week's tutorial as well.